All right, before we go further, we have a review or talk about something that you already know. So valence bond theory, you have learned this in maybe Gen Chem 1, maybe a little bit in Ochem 1. Okay. All right, so valence bond theory. So we use valence bond theory to describe how a covalent bond is formed between two atomic orbitals. Right? In valence bond theory, there are two types of bonds. We have a sigma bond that's come from head-to-head overlapping, and we have side-to-side, that type bond. Okay. Valence bond theory basically look at an overlapping between a pair of atomic orbital, so either S and S, P and P, right? But it's assumed that all electrons are localized, so localized in these orbitals. True for some molecules, but you have seen cases we have that molecules have conjugation, right? Valence bond theory cannot explain the behavior of those type of molecules. Okay, to be able to explain the behavior of those molecules, we need a new theory, and you probably have heard before this we call molecular orbital theory or MO theory. Okay, MO theory looks at electron of the entire molecules, regardless of if they are localized, delocalized, doesn't matter. They look at the whole molecules, and MO theory also takes conjugation into account, and you will see this how it works later. All right, but before that, I have to explain the electrons as a wave. All right, so we're going to look at the electron as a wave. And speaking of wave, I think you know this property of wave. So if let's say I have wave passing through two slits, these two slits will act as a new sources of waves. Okay, and they can interfere right there. Right, they get on each other, interfere. If the two waves are on the same phase, I think you know, so they add up, the amplitude get add up. Right, so we call this constructive interference. On the other hand, so in opposite direction, if the one of them have an opposite phase, so they kind of cancel each other out. In this case, we call destructive interference. Okay, this one just to reinforce it what I just said. Anyway, so molecular orbital theory look at electron as a wave. So let's say if I have two s orbitals overlapping, right? So they have wave, they can be in any phases, right? So let's say they are on the same phase. This happen, you're gonna get a bigger lobe of orbitals. Okay, I use color to show like different phase. So let's say if they're on the red phase, you get a red. If both of them are on the blue phase, you get blue, and it doesn't matter. But same thing here. All right. So this one they constructive interference, and we call bonding. And this is sigma bond, so I put sigma right there. All right. Now, if one of them are on different phase, this is what happened. They don't like each other, so they try to kind of like turn away to the opposite direction, and in the middle we get a node. We call orbital node, which is a point or plane of zero electron density. There's no electron right here. All right. So in this case, we call it anti-bonding. They interfere destructively. So we're gonna put sigma and star, as a symbol. All right. And of course, bonding is more stable. All right. So basically, these are the possibility of two s orbitals overlap. All right. And there are two electrons. So one each from each orbital. To add on here, you can add so up and down. We add from the lowest energy orbital. I think you know that. All right, now p orbital, same thing. Look at this p orbital as a wave. So let's say if these two p orbitals are on the same phase, you get constructive interference of bonding. And I put pi right here because it's going to be side to side overlap, so you get pi bond. Okay, and you can also get if one of them is not on the same phase with the other, you get an anti-bonding. We put pi star, and you can see that the color are different. So red at the bottom doesn't match with blue, red doesn't match with blue. All right. In each p orbital contain one electron, so we have two electrons total. So I'm going to put at the lowest energy orbital up and down. Here we go. Okay. All right. So the molecular orbital of ethylene goes something like this. It's just review. Don't worry about it. It's just review. Right. So in ethylene, there are two p orbitals on each carbon, right? And then they can overlap constructively. They're on the same phase, or destructively. Right. So you get pi and pi star. Then so that's pretty much it, right? So constructive interference or destructive interference, pi or pi star, sigma star, and that's pretty much nothing else. Now I'm going to adding electrons. Okay, in ethylene, how many pi electrons are there? Two, one each. Okay, so one here and one there. When they overlap, so we have two of them going to put together in on a pi. That's a bonding pi bond. Okay, we call the lower energy right here HOMO, which is stand for highest occupied molecular orbital theory. The highest occupied molecular orbital, no theory, no, that's HOMO. And at the top right here, we call LUMO, which is the lowest unoccupied molecular orbital. All right, so just review. All right, next video, we're going to look at the molecular orbital of a conjugated pi system.